It's basically like when you take a number and divide it by its opposite. Like if you took 8 and divided it by -8, that would reduce down to -1. Whereas if you divide like 8 by 8, it reduces down to +1. So if you completely cancel a factor out, it's just gone. If you divide a factor by its opposite, then it reduces down to -1. Okay, so really nothing 1 through 4 that we want to see? Those are all good? All done? Okay. All right, so let's move to that next section, 5, 6, 7, 8. Anything in there? 7? Okay. So let's start with 7. So when we do this section, I want to compare 7, which are the expressions, to the like 19 through 24, which are the equations. So 7, let me start with this. What is that? 3 over. Okay, so we're going to start with some very, very important clarifications here. So this is an expression. The ones from 19 through 24 from section 8.6, those are equations. Can anyone tell me the, hopefully, most obvious difference between expressions and equations? Equal sign. Good. Equations have equal signs. Expressions do not. This does not have an equal sign. This is just an expression. We've got addition and subtraction in the middle. So when you are answering a question that is either dealing with people, gentlemen. Okay. Expressions versus equations. Expressions, do you remember what the directions will say on expressions? Like what verb will you be told to do with expressions? Nope, not with expressions. Simplify. With expressions, you will be told to simplify. With equations, you will be told to solve. Good. So 2 major clues. Whether you're told to simplify versus solve, that should tell you if you're looking at an expression versus an equation. And then equations, they have equal signs. You're eventually going to get to the point of like x equals something or like a equals something. With expressions, okay, another very important thing here. Let's say I had a number. Let's say it was 2. If I multiplied 2 by another number, does it change it? Yes. If I multiplied 2 by another number, does it change it? Yes. Let's say I had something like 2 equals 3x. If I multiply both sides of the equation by a number, does it change that equation? No, it is perfectly okay to multiply both sides of the equation by something. So that's what people get mixed up. They start to confuse the stuff that we did with the expressions in 8.2 with the equations that we did in 8.6. Okay, so I'm going to walk you through kind of very slowly and explain exactly what we're doing here. So what we're supposed to be doing is getting the same denominator so that they all have the same denominator and you're actually able to add them together, because you can't add and subtract these the way they're written right now because they have 3 separate denominators. So what our first thing to do, both with 8.2 and with 8.6, the first thing we're supposed to be doing is coming up with an LCD. So look at all the denominators, this one, this one, this one. My advice to you would be to kind of move from left to right and just pick up all the pieces that you need, because the LCD needs to be at least as big as these 3 denominators. You need to have all of these pieces that you see right here. So because of this y, my LCD needs to have a y, right? Because of this 7, my LCD needs to have a 7. Okay, so move here. Do I need to add in a 2? Do I have a 2 yet? No, so do I need to add in a 2? Yes. All right, how about a y squared? Do I need a y squared? No. I already have one y, so what else do I need? Just another copy of y. So what is my LCD? 14y squared. Okay, here's what people get mixed up between the 8.2 stuff and the 8.6 stuff. A lot of people try to just multiply everything by 14y squared. Can I just multiply everything by 14y squared?
Absolutely not.
No. If you multiply an expression by 14y squared, will it change that expression? Yes. Are we supposed to be changing the expression? No. We're supposed to have the same expression, so we need to make sure that whatever we're doing doesn't actually change it. What is the only thing that you can multiply by and not change something? 1. So technically we have to make sure that we are only ever multiplying by 1. All right, so that's what we're going to do. So our goal, kind of show you guys what the end of this looks like. My goal is to get all of these to have the same denominator, which is the LCD that I just found. Okay, so we are looking to make sure that we only multiply by 1. So look at this denominator, the way it is originally, compared to what I want the denominator to be. What is missing from this one that this one has? 14y. Good. So you essentially are going to just multiply in that 14y, but what else do you have to do to make sure you're not changing the expression? Multiply on top too. Okay, this part is very important. What is 14y divided by 14y? 1. Okay, again, what is 14y over 14y?
1. Now y.
If I multiply by 1, does it change the expression? No. Is it going to look different? Yes, but is it going to be different? No, it's going to be the same expression. Think if you had like 1/2. What if I multiplied 1/2 by 3 over 3? I would get 3 over 6. Do these numbers look different? Yes. Are they different? No. So if I multiply, same thing, top and bottom, it's not going to change it. It's just going to look different. So this numerator becomes 14y. All right. Don't cancel anything here. That'll just undo what we just did, and we did that on purpose. Okay. This one, what is this denominator missing that this one has? It's a 7 right now. What do I need to multiply it by to get this denominator?
2y squared.
2y squared. Good. So top and bottom, 2y squared over 2y squared. What are you technically multiplying by? 1. If you multiply by 1, does it change the expression? No. Okay, what's missing with this one? 7. Good. So you multiply by 7 over 7. Again, technically multiplying by 1, it's not going to change anything. So this numerator becomes 4y squared. This numerator becomes 21. So take a look at all of these denominators. They're now all exactly the same. Because they are exactly the same, now I'm allowed to add and subtract these numerators. Do any of them have a common term? Are any of them the same variable part? No. So I can't combine any of them, but I just kind of write them across like this. Put them all in one numerator. There's nothing beyond this point that we can simplify or cancel any further. You would just leave your final answer like that. Okay, so with expressions, when you're adding and subtracting, once you get them to the point where they're all over the same denominator, then you're good. That's what they mean by simplifying those. Okay, anything else in the 6 or 5, 6, 7, 8 range? Five, 6, 7, 8? No? Okay, so let's start looking at graphs. Anything 9 through 16, all of the graphing stuff, 9 through 16. Sandra? Which one? 10 and 16. Okay, so let's start with 10. 10 and 16 are actually pretty similar because of something weird that happens with both of them. So for number 10, it says, what is the equation of the vertical asymptotes? Remember, vertical asymptotes happen when you set the denominator equal to 0. So this starts off as x plus 1 over x squared plus 3x plus 2. So what we're going to do, and you guys will see more of these because I'm going to do some more graphs for you. You've got the numerator that gives you x-intercepts, and then the denominator that gives you vertical asymptotes. So they're asking about vertical asymptotes. This is going to have to be factored, so let's start by factoring it now. So this numerator is x plus 1. If I factor the denominator down, I start with x times x. What multiplies to positive 2 and adds to positive 3? 2 and 1. Good, so I get x plus 2, x plus 1. Do you see anything that we could do up there? These will cancel. What's technically left behind in the numerator? 1. Good. So I've got 1 over x plus 2. So that means this equation is equivalent to this equation. I just reduced it down by factoring and canceling. So now when the question asks what is the vertical asymptote, we're taking the denominator and setting it equal to 0. So what is the vertical asymptote for this graph? Negative 2. Good. So you'd write x equals negative 2. Okay, so that's 10. 16 is really similar, and it has this weird factoring and canceling thing. So 16, we've got x squared plus 5x minus 6, and then over x minus 1. So same thing. Numerator gives you your x-intercepts. Denominator gives you your vertical asymptotes. So we can still factor this down. The numerator is x times x. So now for this one, what multiplies to negative 6 adds to positive 5?
6 and negative 1.
Good. 6 and negative 1. So again, with this one, what can happen here? Cancel these, and this is just equal to x plus 6. So this is actually weird. I will not give you one like this on the test where it ends up reducing down to a line, because this is just a line. Do you guys remember like y equals mx plus b? Yeah. This is just y equals mx plus b stuff right here. So I will not give you one, but just to show you, remind you of how you graph these. Do you guys remember plotting these using the y-intercepts and then the slope? So if this is an mx plus b form, what is the y-intercepts?
1.
Nope. 6. Good. 6 is the y-intercept. So we go up to 6. You'd plot a point right there. And then what is the slope? Think mx plus b. Bless you.
Thank you.
What is the slope? 1. Good. So there's technically a 1 in front of the x. So that means we go up 1 over 1 for another point. So this just turns into a line. One more time, I will not give you one that just turns into a line. So we probably should look at one of these where you actually figure out how to do the x-intercepts, vertical asymptotes. So what else do we want? I want definitely something 11, 12, or 13.
13.
So pick one of there. 13? Okay. So first of all, I'm going to put this up on the screen for you guys so you can see the difference, because 8.3 and 8.4 are both graphing. So I want you to be able to see the difference between whether you're doing 8.3 graphing or 8.2 graphing, because the techniques are slightly different. So look at 11, 12, and 13. Okay, first thing that ties them all together. Actually, I want you guys to look for patterns. What do 11, 12, and 13 have in common that 14, 15, and 16 do not?
There's no x in the numerator.
There's no x in the numerator. Good. That is the most obvious thing that stands out about 8-3. See how they just have numbers? The numerators are just numbers. Those are called reciprocal functions. And the way I defined those, so 8-3, we called those reciprocal functions. And, whoops. So they look like this. They had just some number, so let's call that number a, and then over b of x, and then there was usually some sort of constant at the end like that. Okay, so just a number, linear factor down here, and then some sort of constant on the side. The 8-4 functions, we had some sort of expression in the numerator, some sort of expression in the denominator. But for 8-3, this is just a number, and then you're usually going to have some sort of number at the end. But this is the easiest way to tell them apart. If it is just a number in the numerator, then you're doing it the 8-3 way, where we do vertical asymptote, horizontal asymptote, and then transform those 2 points. So let me give you an example of that. So 13, I think we said we wanted to look at. So 13, let's see. Okay. All right, we got 3 over x minus 1 and then plus 8 on the outside. So 4 things that you guys need for these from 8-3. You need vertical asymptote, horizontal asymptote, and then you're going to transform these 2 points. Vertical asymptote. What do we have? Not for the vertical. 1. Good. So the vertical comes from the denominator. You set the denominator equal to 0, which always means you've got the opposite of what you see down here. So the vertical would be x equals positive 1. How about the horizontal asymptote? Y equals 8. Good. That's always the number on the end there. And it stays whatever sign it looks like. So if you see a positive 8, it is a positive 8. So now these transformations. So start with these points. They're very easy to remember, or they would be a great thing to put on your note card. So start with the x transformations. Because of the x minus 1 in the denominator, what am I doing to both of these x values here?
Adding 1.
Adding 1. Good. If I see x minus 1, that means I add 1 to my x values. So this becomes 2. This becomes 0. And then my y goes through 2 transformations. What's the first thing that happens to these y values? Multiply by 3. And then?
Add 8.
Add 8. Good. So 1 times 3 plus 8. Negative 1 times 3 plus 8.
How did you get the 2 and 0 again?
So the x minus 1, remember you always do the opposite? So because there's a minus 1, you're adding 1 to these 2 x values that you started with. All right, are you guys good on these details so far before I start plotting? Good, okay. So set up equation like this. So x equals 1, you're just going 1 unit over. That's a dotted vertical line right there. And then for y equals 8, I'm going to scale my y-axis by 2. Scaling is perfectly fine. Just make sure that you make me a little note. Like if you're scaling by 2 or scaling by 3, just make sure you write it on there like I did. So 2, 4, 6, 8. So that is your horizontal one. And then we've got points to plot. So we have 2, 11. So that would be like right there. And then 0, 5 would be right there. Okay, so remember these take on those like boomerang sort of shapes. So you follow along, right along the vertical asymptote. As soon as you hit that point, you curve along the horizontal asymptote. Same thing here. Hug the vertical asymptote, hit the point, curve along. Whoops, I went under it. It looks something like that. Okay, so that's the graph itself. Any questions or issues with the graph itself? No? Okay, domain and range. These ones should be really easy. It's just x is not equal to, y is not equal to. So if you look at the domain, all of the possible x values, x will take on every single value except for what?
1.
1. Good. Just that dotted line is the only one that your graph will never actually hit. And then for y will take on every single value except for what? 8. Good. So you will be asked for domain and range on those. So make sure you know how to answer. As long as you're able to come up with your vertical asymptote and your horizontal asymptote, you should be able to come up with domain and range. Yes, sir?
So technically you don't have to use your calculator to figure out the points?
No, these ones with 8-3, you do this. So like these steps are still pretty much the same, but these are always the same. It's those boomerang shapes. It's the same pattern every time. But with 8-4, there are so many different things that could happen that you just pretty much let your calculator. Because we had some that kind of looks like this, but then we had some, remember the quiz that you guys had where it was like a line like this and they kind of went like this and like that. Like it could do anything with 8-4. And so that's why we've got your calculator doing the bulk of the work after we find the asymptotes. Okay, any of the other 8-3 ones, 11, 12, 13? No? Okay, how about 14 or 15? Pick one of those.
14.
14? Okay. Okay, so here I will walk you through how the 8-4 process works. So we've got 3 things that you need to find before you plug things into your calculator. So we've got x-intercepts, vertical asymptotes, horizontal asymptote. Okay, so first thing, x-intercept, then vertical asymptote, and then horizontal asymptote. So you need to find those 3 things, and then you can let your calculator show you what the actual shape looks like. Okay, so x-intercept. How do I find my x-intercept? Good. So take the numerator, which for us is 5x, and set it equal to 0. Numerator gives you your x-intercepts. Denominator gives you vertical asymptote. So 5x equals 0. That gives us what as an x-intercept? 0. Good. If you divide both sides by 5, 0 divided by 5 is still 0. So when you're plotting, it would look like that. It should be right at the origin. So the x-intercept is just a point. So setting the numerator equal to 0 just gives you a single point that your graph is going to go through. All right, and then next your vertical asymptote. How do we find vertical asymptotes?
The bottom to 0.
Good. Denominator equals 0. So what does that give us? -1. Good. Vertical asymptote is a line. We go to -1, put a dotted line in like this. Okay, horizontal asymptote. Here's the fun part. These rules are very strange. They have to do with the degree of the numerator versus the degree of the denominator. So with this one, what's the degree of the numerator? 1. Denominator? 1. Okay, so they're the same. What is the rule when the numerator and the denominator have the same degree? Take the coefficients. Good. So what's the coefficient for the denominator? It's technically a 1 there, so we take the ratio. So our horizontal asymptote would be y equals 5. Let's recap the other ones really quickly. So if they're equal, we take the ratio. Are you guys comfortable with that one? Okay, what if the numerator's degree is the smaller one?
There is none.
It's 0. If the numerator's degree is the smaller one, then it's 0. Okay, so you would just write that, y equals 0, and then plot it on the x-axis. What if the numerator's degree is the larger one?
There's none.
Then there's none. Okay, very important thing to point out for Monday. I want you guys to make sure you do this. If there is no horizontal asymptote, write no HA. Like at this part, write no HA, because that tells me that you know the rules. You figured out that there was no horizontal asymptote, because otherwise what could have happened? I think I mentioned this the other day. You might have just forgotten about the horizontal asymptote. So writing down no HA shows me that you remember that there's supposed to be a horizontal asymptote, you remember your rules, and you recognize that with this particular function there is no horizontal asymptote. So make sure you write that. That'll be worth a point if that situation pops up on the test. Okay, so for us we've got 5. I'm going to scale again. Make sure you write it if you do scale. Okay, so those are our asymptotes. We've got x-intercept, vertical asymptote, horizontal asymptote. Once you get all of this work written down and then all of this stuff plotted, then you can just let your calculator do the rest of the work. All right, so I will show you, remind you how to plug those in. So open up either a new document altogether, or you can just add in just a new page to whatever you're working on. So graph page looks like this. And since 8-4 is all the fractions, you want to make sure you know how to input those fractions. So hit your blue key and then the little division sign so it pops up and has a little separate numerator and denominator. It's your fraction button. So 5x for the numerator, x plus 1, and then just hit enter. So one thing, so see how like that second boomerang shape is like really not on the screen at all? I want to show you guys one additional thing if this ever pops up. You know where your menu key is? Over on the right here? Press your menu key. And then we want to zoom out a little bit. So what do you think we're going to press? Window/zoom. Then what?
Zoom in, out.
Zoom out. Good. So it's just menu 4. That's easy enough to remember. So just click and then it'll zoom out, and then you'll get a much better picture of what that graph is supposed to look like. Because it used to only go up to 7 and now it's going up to 15. So it gives you a much wider view of that. So you can see all the pieces that we had. We plotted our x-intercept. You guys see your x-intercept right there through the origin? And can you see your vertical asymptote of -1 right about there? And our horizontal asymptote of 5. Okay, so if for some reason that happens and you don't really get a very clear picture, you can always zoom out and get a better picture of the graph. So the last thing you have to do is just look at the picture and just kind of sketch out what you see there. So it should look something like that. Okay, so that would be your final answer. All right, anything else on 14? 14, 15, 16, anything in that general vicinity? No? Good. All right. I feel like we're gonna focus on 19 through 24. What do we want to see in there? 22? Okay. Start with that one. Oops, this should be a -5. Okay, so equations. We did expressions. I want to touch on equations really quickly. So this is our expressions one. This is the first one we did when we were adding and subtracting all these terms together. And our goal was to make sure that we could get them to all have the same denominator so that we could add them all together. Okay, there was no canceling that was happening. We were turning each of these denominators into the LCD so that we could add them together. Because it's not an equation, we can't multiply by the LCD. We can only multiply by what's technically 1 because we can't change the expression. Our first step with these was still to find the LCD. Our first step with this is also to find the LCD. So with the equations and with the expressions, our first step is still the same. We need to know how to find those LCDs, but then what we do with them is very different if you're dealing with an expression versus dealing with an equation. So here we have an equation. This is the only denominator that we have. So what is our LCD here? R. So our LCD is going to be R. So the way that these work, you take the entire left-hand side of your equation, you take the entire right-hand side of your equation, multiply the left and the right by R, or whatever the LCD is. So I've told you guys this before. Humor me when you're doing these. Write them all out. Like write it times every single piece so you can see all the canceling happening and see what's left over. So when I multiplied the left-hand side by R, it distributed to all these pieces, and then that's multiplying the right-hand side by R. So let's see what's left. What is this first term?
R squared.
R squared. Plus, and then what happens with the second term?
6R over R squared.
6.
Just 6, right? These would cancel out.
Oh, wow.
And so I just have a 6. And then how about that third term?
Minus 5R.
5R. What's 0 times R? 0. Okay, the left-hand side I think is what's going to freak people out. What should you do with that left-hand side?
Move it over. No.
Okay, it's already all over.
0. Wait, never mind. I'm not.
We're going to factor it, but not quite yet. I think this is probably what's freaking people out about 22. Yes, these guys are not in the order that we're used to seeing them in. We're used to seeing it in standard form, which means the squared term, then the linear term, then the constant. So we should have R squared minus 5R and then plus 6 equals 0. So get it back into its normal form because otherwise we're not used to factoring if it's not in this form. Okay, so start with R times R is going to give us our R squared. Okay, 6s and 5s. People have a really hard time with 6s and 5s. Multiply to positive 6, add to negative 5. Good. Minus 3, minus 2. Good. 2 negatives multiply to a positive, but they add to a negative. So for my R values, I would get R equals 3 and R equals 2. Okay, with equations, these are the ones we have to check for extraneous solutions because it does not matter how well you did this problem. Doesn't matter how confident you are about your algebra skills. You could be the greatest mathematician in the world, and these could still pop up to be extraneous through no fault of your own. We've talked about this before. The 3, if I go to plug the 3 back in, is 3 an extraneous solution? No, this denominator would be 3, and 3 is a perfectly acceptable denominator. What if I tried to plug the 2 in? Nope, also perfectly acceptable. What would be extraneous if I came up with it? 0. 0 would be extraneous because I can't have a 0 in my denominator here. Okay, so that's 22. What else? 19 through 24. 24? All right, R plus 2 over 3R. Okay, so this one we've got a little bit, more complex denominators. So we can gather up the LCD here. I told you this with the expressions. My advice would be just to go from left to right and just pick up every piece that you need and then leave out the ones that you already have. So for our LCD, start with the first one. It's definitely going to need everything that you see from the first one, and then you can move from left to right and see what else you're going to need to pick up. So we need these. Do we need an R minus 2?
Yeah.
Okay, important question for you. Will this R from the R minus 2 cancel this R? No. So we need the entire R minus 2 and we need the R. How about this 3? No, we don't need it. We already have a 3. This 3 will work for this 3. So this is our LCD. Before I do anything else, are you comfortable with the LCD? Yeah, okay. So we're going to multiply the whole left-hand side, multiply the whole right-hand side by that LCD. And again, humor me. Just write it out because you guys will try to do it in your head, and for a lot of you, it just doesn't work. Okay, so we got this. and then write down, like physically cancel out everything that cancels. So the 3r will cancel here. The r minus 2 will cancel here, and then the 3 will cancel here. So be super, super careful with this one when you're simplifying up what's left. On the left-hand side of the equation, we have r plus 2 times r minus 2. You guys should recognize that as difference of squares. What does r plus 2, r minus 2 FOIL back out to? R squared minus 4. Good. We should recognize that as the difference of squares pattern. Okay, and then equals. Next piece, we have a 3r times an r plus 4. So really that 3r is just going to distribute to the r plus 4. So you'd have 3r squared plus 12r. Okay, next one, be careful. Look at the subtraction. The subtraction makes this a little bit complicated. So I've got a negative 2 times r minus 2. So I'm going to take a negative 2r and distribute to these two pieces. Okay, so what's the first term that I would get? So I'm taking a negative 2r and distributing to these two pieces.
Negative 2r squared.
Negative 2r squared, and then be careful with the next one.
4 plus 4.
Plus 4r.
Wait.
Because I've got an r right here, so I have negative 2 times r and then distribute to the negative 2. Okay, so here's where I'm at so far. Any questions, any concerns? Are we good? Okay, so all of the denominators canceled out because I multiplied by the LCD. And so now we're going to start going through combining up like terms. So on the left-hand side, there are no like terms. On the right-hand side, I have a 3r squared minus 2r squared, which is just an r squared. And then I have a 12r and a 4r. So that is 16r. Okay, do you guys remember this? Do you remember what I said the other day? If you have the exact same term on both sides, what happens to these terms? They cancel. Good. If I were to subtract an r squared from both sides, they would both be gone. So I have just a negative 4 on the left and then a 16r on the right. Divide both sides by 16. What does that reduce down to?
Negative 4.
Negative 1/4. Good. The numerator is smaller. So that reduces down to negative 1/4. Check my denominators. What's the domain restriction for this denominator? What can't I plug in over here? 0, right? And this is not 0, so we're okay so far. What could I not plug into this denominator? This is an r minus 2. I can't plug in 2, and this is not a 2, so we're still okay. This denominator is 3. Will 3 ever be 0? No, so this one doesn't have any domain restrictions. So this one's good. It's perfect. It's wonderful just the way it is. Okay, anything else, 19 to 24? Do you guys want to do the inequality so we talk about the true and false check really quickly?
Yeah.
Get that? Okay, so 21 is our inequality. Let's make sure we do that one. So 7 plus 2 over x is at a less than negative 5 over x. Okay, this one has a very specific process. This would be a good thing to put on your note card so you know the steps that you guys are taking with this. So step one, we are going to find what we call domain restrictions. And we've been talking about domain restrictions with the equations. They're anything that make the denominator equal to 0. Okay, so our denominators can't be 0. We're going to cut out anything that would make the denominators equal to 0. So look at these denominators. Can you think of any x values that you would plug in that would make the denominator 0? What would make this one 0? 0. What would make this one 0? 0. Okay. Keep in mind that even though 0 is the most common domain restriction, it's not the only possible domain restriction. What if this was an x plus 3? What would the domain restriction be? Negative 3. Good. So keep in mind that it might not just be 0. It's most common, but it might be something else. Step 2, the way I wrote it in the notes, was to solve the related equation, meaning turn the inequality into an equation and solve that. Okay, and this is a much easier equation than some of the other ones you guys had on the page. Look at the denominators. What is the LCD for this equation? X. The only denominator is x, which means x is the LCD. So I'm going to multiply everything through by x, everything on the left, everything on the right, which means I'm going to distribute the x to every piece. And then you can see that these x's will cancel and these x's will cancel. So what does the left-hand side of my equation become? 7x plus 2 equals negative 5. Good. So this is actually a really pretty basic equation to solve. So we get 7x equals negative 7. And then x equals negative 1. Okay, let's run through the steps again. Step 1, domain restrictions. Are you guys okay with that step? Okay, step 2, turn the inequality into an equal sign and solve the equation. Are you okay with that step? Okay, step 3 and 4 kind of go together. Step 3 says to take a number line and put anything that step 1 gave you and anything that step 2 gave you on that number line. Okay, so whatever numbers you have here, whatever numbers you have here. So it's possible that 0 might not be on the number line. Okay, 0 isn't like an automatic figure on the number line. Whatever you get from these 2 steps, go on there in numerical order. You will mess up your entire answer if they are not in numerical order, which means negatives first, then 0, then positives. So that's your number line. Good so far?
Yeah.
Okay, so we're going to plug everything in here. I'm going to show you guys how to work this. So we are going to take whatever value we want. So any number right about here, some number smaller than negative 1. Negative 1.1. Beautiful. Store that in. His name's McKenna. He graduated a few years ago. He just peeked in the window. All right, so we're storing negative 1.1 in as x. So whatever you want to store in here, you store it in there, and then you type in the inequality. Okay, so type in the inequality, 7 plus 2 over x, and then your equations, your inequality symbols, hit your blue key, and then the equal sign right underneath. And you open up, get all your less than, your greater than, whatever you need. Negative 5 over x.
How do you get the arrow to, like, for the first part?
Hit the blue key and then right above the 9. See where it says STO and then has that arrow?
Yeah. And then what do you put in X?
X. Yep, so it's always the number first, then the arrow, and then X. Okay, so we tested that out and we got false. So just put a big F or false or whatever on that part of the number line. Okay, this is tricky because this is just one number apart. So pick something that's going to be in here. Negative 0.5. Okay, so if we took negative 0.5, store that in as X. And then remember, you do not need to retype, just kind of arrow up until you've got it highlighted. Enter 1 to copy it, and then enter again to test it. So this one turned out true. Okay, something bigger than 0. Guys, stay with me for 10 more minutes. Something bigger than 0. 1. Okay, so take 1, store it in as X, and then one more time, arrow up, copy, paste, and test that one. So that one turns out false. Okay, so this is what your number line looks like. Let me clarify something. Your number line is not your answer. This is not your answer. Taking the number line and writing in an equality, that's your answer. So this piece right here, that's the region that ended up true. So let's write that as an inequality. People have a lot of trouble with this. So what are we starting with? Negative 1 is less than x, which is less than 0. Okay, when you have a 3-piece, 2 things. These are always in numerical order. Negative 1 is the smaller of the 2 numbers. 0 is the larger of the 2 numbers. These inequalities will both always face in the same way. They will both be less than. That's because the 3-piece, it's read like this. X has to be greater than negative 1, and also x has to be smaller than 0. So it's read both ways. The x starts in the middle. So that is our inequality. Okay, any other requests 19 through 24? No? Okay, let's pick 25, 26, or 27. Sure. Set them up really quickly. Okay, so remind you guys of some of the alliteration that I gave you. So 25 says y varies. So if it says y varies, or a varies, or m varies, whatever is varying, that is your main variable, and it's always in the numerator. Okay, so we know that. We've got y varies. And then for 25, it says inversely. Do you remember the alliteration that I told you? Inversely means what? What did I tell you? In line. So inversely, it means multiplication, but those aren't alliteration. So inversely means in line with x. So then we multiply by x1, x2. So this is how you'd set up inverse. Okay, I'm going to go through and set them all up for you, and then we can pick one to go through and solve. 26 says m varies, so that becomes your main variable. M1, M2. And then m varies directly as n. Think alliteration again. Directly means what? Division. Good, so we divide by n1, n2. So that's the setup for 26. Like I said, we will pick one of these to do. 27, so r varies jointly. The jointly, that's the only time they don't literally mention the word direct or mention the word inverse, because even with compound, you have one of each. So it'll say like directly as x and inversely as z or something like that. So 27 says r varies, so that's your main variable, like that. And then jointly. Where do they end up if it's jointly? What do we have for 27? Where do the other 2 variables end up if it's jointly? In the denominator. Jointly is double direct variation, so they both end up in the denominator. Okay, which one of these do we want to go through and finish? Any preference? 27? Okay. So 27, suppose R varies jointly as S and T. So again, joint variation is double direct variation, which means they are both in the denominator. If S equals 20, when R equals 140 and T equals -5, find S when T equals 7. Whoops, sorry, T is 2.5 and R is 7. Okay, so that is your setup. We got all the pieces that we need here. So since your variable's in the denominator, I would cross multiply, and you can simplify this before you cross multiply. So this 140 over 20, what does that reduce to? 7. Good. The zeros would cancel, and then 14 divided by 2 is 7. So 2 different techniques I'm going to show you. We've got 2.5 times S. So with these, anytime that your variable is in the denominator like this, I would cross multiply. I think that's the best way to get the variable kind of safely out of the denominator. So cross multiply here, you will have 17.5S equals, and then cross multiply here, you'll get -35. So to get the S by itself, we're going to divide both sides by 17.5. So you could use a calculator for this, but it does reduce down to -2. Okay, so that's one way, cross multiplying. This way also has kind of a unique way that you could solve it. An equation means that these two things are equal, right? Like this expression must be equal to this expression. Notice that the numerators are equal. So if you've got two separate fractions that are supposed to be the same fraction, if the numerators are equal, what does that mean? The denominators must be equal. So you could also just set up a little equation where you set the denominators equal to each other. And if you solved this, you would also get -2. So 2 different ways. I'm sure there are other, I know some other people had different ways besides cross multiplying. I think cross multiplying is probably the easiest. Okay, any other questions? Yes, ma'am.
How do you know which number is like at 1 or at
Oh, that doesn't matter at all. Doesn't matter at all, no. Okay, any other questions on the practice test? No, okay. So we can just relax for a couple minutes here. If you've got your practice test, I want to see it. I can put you on my list.